Now, arithmetic, elementary school math is called arithmetic. That dealing with numbers, and that's where you have the order operation. So you have this PEMDAS. PEMDAS can teach you how to deal with numbers. But now in algebra, we're not dealing with numbers, we're dealing with symbols. Since we are dealing with symbols, we need to know the rules. So that's why when we start algebra, that's the first thing we learn, the rules. And also, like last time, as I explained to Morrigan, that math is different from other kind of science, like different from physics or chemistry. The reason for that, in most called physical sciences, they use inductive reasoning. That means you have experiment, and from those experiments, you find a pattern, and then you generalize it. Okay, like you see the sun came up yesterday and the day before yesterday, and the day before yesterday, and you generalize that, and to that, the sun will come up every day, which actually, so far so good. But we really don't know if that always true. We just have some idea, have some high probability it will be true, but we really don't know for sure. It's called inductive reasoning, and sometimes we do find that it's wrong. Like for example, if you go out your home, you look at your neighborhood, you see the earth is flat, and you just kind of go to your, maybe your city or your town, then you still see flat. And you go to see the States, you see the flat. Okay, unless you live in close to the ocean, that's all you see. You see everything's flat. So then you can generalize that. You say, okay, the earth is flat. And we know this is not true. And the reason we know it's not true because, well, first of all, we are told, well, we learned that it's not true. But even people didn't tell you, if you get a chance to go to the coast, have you guys been to the coast? Either West Coast or East Coast? Go to the ocean, huh?
I've been to Lake Michigan.
Perfect.
Okay, yeah, me too.
And do you notice, actually it's not flat, the horizon?
Yes.
So it's actually a bit curved, right?
Yep.
And that's actually what the ancient Greeks saw, because the Greeks living, by the ocean. So they saw the earth actually is not flat. And another thing, they realized that earth is not flat is because when you see a ship, a big ship come towards you, you first see the, what do you call that? The mast, something like sticking out from the boat. And you see that first before actually you see the ship, the body of a ship. So that's only happens if the earth is not flat. So the Greeks knew earth is not flat. But many people live in inland, like the Chinese culture, because the Chinese, most of them live inland, and they thought that the earth is flat. So that to teach you that inductive reasoning has a problem, is that we can see what's going on in the past, or our limited knowledge, or in terms of science, our limited experiment. We make a prediction, and that prediction may not be right. So that generation might not be right. So this is a nature of most sciences, and especially when we're dealing with like the pandemic, with medicine and all of that, where most time we use inductive reasoning. Like that's why we have the vaccine, and we have trial the vaccine, then we see whether or not it's safe. So we don't know until we have enough data. And that's the problem with inductive reasoning. And that's why you see things change. either in physics or chemistry. Science, math itself is very different. Math is based on inductive reasoning, is that you come from a general to specific. So if you follow the logic and you can establish the core theorems. And once you establish that, it is pretty much, you can guarantee it's true. So the only thing might not true is the basic assumption. So in math, in algebra, either in algebra or geometry, the basic we call the axioms. On top of that, we can prove theorems. And on top of that, then you can theorem is based on theorems. So you can just build up the whole thing. And as long as our basic axioms are right, then all the theorems are true. So that's why you didn't see nothing much change. Say for geometry is over 2,000 years old. Almost all the theorems are still true. Now algebra is about 1,000 years old. So most of the things we know about algebra are still true. That's because there are different kinds of reasoning. So inductive reasoning has that the characteristics that as long as the basics, the axioms is true, then everything on top of that is fine. Good.
Okay.
Have you guys learned the geometry?
I've learned like very basic geometry, like angles and stuff
Okay.
like that, you know, cute.
Right. How about Jade?
Same thing.
Okay. Well, so like in geometry, one of the basic thing is about the sum of the all the angles of triangles, and the sum is 180. Good.
Okay.
So everything on
Got
top of that, we can prove that is true. All the theorems. This is a very basic assumption, and that turns out it's only true when we're dealing with a flat surface. Good.
Okay.
Now, when you're
Yeah.
dealing with a sphere like on Earth, then you end up with something that the sum of all that, you could have something like this. You have right angles on all three angles. So if you right angle on all three angles, you actually end up with 270 instead 180. So things different is on the surface of sphere. Good.
Okay.
And that came up with totally different, the new kind of geometry is called non-Euclidean geometry. Have you heard of that?
No, I haven't.
Nope.
Okay. Normal geometry you learn is called Euclidean geometry. The reason we have that name is because he wrote a book called Elements. Actually, that's many volumes of the book. I think 13 volumes. He was talking about all the theorems. And one of the Euclidean geometry, that is one of the basic kind of basic assumptions. But so far, that's the only one. They found that in other situations, things are different. And the rest, there are about 10 of those. The other 9 is still true. Nobody has overturned that. Good.
Okay.
So you see, now you see the math is different from all other sciences. And that in a way, that's what I like math, is because the logic is pretty much watertight. As long as the basic assumptions are true, then everything, all the theorems are true. So that's actually what happens with algebra. Now, so algebra starting with, first of all, the numbers we're dealing with are called the real numbers. Are you good with that? What is a real number?
Yeah, I think so.
Okay, how about you, Jet?
Yep.
Okay, very good. So real numbers is a set of rational numbers and also irrational numbers. And this is very important in algebra, is because when in algebra you have this number line here. And so far, if you're only dealing with integers, you have holes between, say, 0 to 1, 1 to 0. There is empty space. But when you throw in fractions, but between fractions, you still have holes. And those holes are filled by irrational numbers. So there's many, many irrational numbers. And the most famous, of course, is the first irrational number discovered by human or by mathematicians, or the Greeks, is square root of 2. And another one we know, pi. Pi actually is kind of hard to prove. Pi was proved much later on. This one was proved pretty early. Then you have square root of 3, square root of 5, 7, and those are all irrational numbers. So therefore, when we're dealing with real numbers, there is no empty space between like 0 to 1 or 1 to 2 and 2 to 3. So within H, like here, there are infinite number of real numbers. Good.
Mhm.
And there's something you probably want to know later on. It's called continuous. Continuous. That means there is no gap. And that's the number we're dealing with in algebra. We're dealing with real numbers. And then in terms of operator, we really just dealing with two operators. One is addition, one is multiplication. Now, everything can be turned into either addition or multiplication. For example, you guys learned about exponent, right?
Do what?
Exponent.
Yes.
So like 4 to the third power. 4 to the third power is just a shorthand. It's not a new operator. It just means 4 times 4 times 4.
Mhm.
Oh, yeah.
Okay. So
Yeah.
this is not a new operation. It's just like a shorthand. So really, the in algebra we're dealing with addition, multiplication, and that's it. Good.
Okay.
Good.
And that's also, and we also know multiplication can turn into addition, right?
Yep.
Yes.
Multiplication basically is addition too many times, and that's why we can do a computer can solve all kinds of computations. So basically, what a computer can does is just addition. They just add things together. Good.
Got it.
Okay, so we have that multiplication, addition, multiplication, and then we're going to study what's the property of addition and multiplication, and we'll find something very interesting. Is that so? More against basically this is a little bit repeat of last time, but I think this is very important because this is our basics, the basics. So it's help us really understand the basics. Then we can once we understand the basic things will become much easier. Good.
All right.
Yeah.
So one thing we see is when we're doing addition, 3 plus 5 is the same as 5 plus 3, right?
Yep.
-2 at -3 is the same as -3 at -2, right?
Yep.
So we see that this happens, that works not for all real numbers. So we have this rule, A plus B equal to B plus A. Now, again, you see we have symbols using, because in algebra, that's what we use. We use symbols because we are really interested in the property of numbers. We are not as interested in the accounting. We're not really interested on what is the value. We are more interested in the properties. When you're doing elementary school algebra, like arithmetic, you are interested in the calculation. You want to get calculating right. But in algebra, we are more concerned, what is the property, okay? Does that happens for all numbers? So this is the first one, A plus B equal to B plus A. So in algebra, a symbol represents a real number. We don't know what they are, but as far as the property goes, it doesn't matter, right? Because we say a plus b equal to b plus a. What we are saying is any two real numbers, when you add them together, the order doesn't matter. Good?
Yep.
So it's a long sentence,
Got it.
but in terms of math, algebra, it becomes very, very clear. It's a plus b is b plus a. The same thing with multiplication. A number times another number is the same as the order does not matter, right?
Yep.
Right.
Okay, so this is called the commutative property. Then all we see is this. When you have three numbers, does that matter which two you put together first?
Do what?
When
No.
you, more than, say you get more than two numbers, does that matters which two we add first?
No.
Definitely not, right? We know
Yeah.
that. And that actually happens to all real numbers. So therefore you have something like this. When you have three numbers, you can add those two first, which is exactly the same, basically have same value as the other two first. Good?
Okay.
So this called associative property. That means they are free to associate with anyone. Now, this is also true for multiplication, right?
Yep.
When you have more than two number multiplied, the order does not matter. Good?
Okay. Yep.
Now, what does the order operation tells us? When you say something have the same order, we follow what? Left to right, right?
Yes.
So for order operation in entry school, the order matters, which one go first, but not in algebra. The reason for that is we only concern about addition and multiplication. Good?
Okay. So when you say we're only concerned about addition and multiplication, do you mean that there's no subtraction or division, or is that
Well,
what we're most
we still
focused on?
have, yeah, very good question. We still have subtraction and division, but when you subtract something, like say 7 minus 4, that is exactly as 7 plus -4. Good?
Yep.
So we turn subtracting into addition. Good?
Got it.
And incidentally, this is actually how the computer does. When the computer subtract two numbers, they actually turn one number into the opposite. Then just add them together. Good?
Okay. Doesn't that need to make it like a little more complicated than what it needs to be? Why don't you just subtract it?
Well,
instead of turning it into its
right. It in terms of calculation is a little bit more complicated. It seems, why do we go that step? But in terms the rules, it makes the rules simple.
Oh, good.
Because now 7 minus 4 does not equal to 4 minus 7, right?
Yeah.
So this rule does not hold for that. Good?
Yep.
But if you turn to something like that, then -4 plus 7, the order does not matter.
Oh, okay.
Do you see that?
Yep.
So we make the rule simpler. Otherwise, we'll say, okay, when you do add, you do this. When you do subtraction, you do that. So we add the rules, and that's what we don't want. Because remember, this is we're using deductive reasoning. We want to keep the fundamental truths as few as possible. Good.
Okay.
Okay.
Got it.
Okay. Perfect. And same thing when you do a division. So 4 divided by 7 now. So 4 divided by 7 is not the same as 7 divided by 4, right?
Yeah.
But if we write 4 divided by 7 as 4 times 1/7, then we can turn then the order does not matter.
Right.
Yeah,
we
that
cha-
makes sense.
So we change division into multiplication now. Good.
Okay.
So that's why we actually only dealing with two, addition and subtraction,
Okay,
as
so
far as this rule goes.
okay, so
Okay.
basically you just bend the way you do math to fit the way the rules are.
Right. Yeah. Exactly.
Okay.
Exactly. And you will see later on why that makes sense, because we are really dealing with symbols. Okay.
Okay.
That makes a lot more sense when we're dealing with simple. But if you want just dealing with simple calculations, this a little bit how to say it's a little bit complicated. Then it's not that straightforward, right?
Right.
So in terms calculations, we definitely we don't want to do that. But for the algebra, we play with symbols, and that as few rules as possible help us to do our math. Good.
Okay.
So this actually is for many famous mathematicians, actually they are not good at computations. Like yeah, the reason for that is mathematicians dealing with symbols, dealing with properties. So a lot of them are not, if you tell them say 250 divided by 13, they have to use, they cannot do that in their head. They have to use a piece of paper or use a calculator. But they can do very abstract math. That's what math is. Good.
Okay.
Yeah, hopefully when we
Okay.
later on, when I saw some examples like that, I'll point that out to you. Good.
Okay.
All right. So we
Okay.
have those. Now we're going to something we also take for granted is a number adding 0 is what? Itself, right?
Yeah.
Does not change. Same thing when you multiply 1. Good.
Yep.
So now we introduce two special numbers. One is 0 and one is 1. Those two numbers are very special. Good.
Okay.
Okay. So, and this is called identity. That means nothing changed. The value not changed. And the next one is a number adding its opposite is equal to 0. Good.
Yep.
Like 4 plus -4 is 0, or -7 plus 7 is 0. Good.
Right.
Or pi plus -pi is still 0. Good.
There's a negative pi too. Well, that makes sense. Never
Oh
mind.
yeah, definitely. When you get into algebra, you get positive and negative numbers.
Okay.
So that's the number we're dealing with. We're dealing with real numbers. Now, real numbers could be positive, could be negative. Good.
Yep. I have a
And
question real quick though.
yeah,
It's about pi. Now, a pi has a lot of digits in it,
Right.
and they're not made up, just made up digits. So who came up with that?
that's a good question. Well, we'll talk about pi maybe next time.
Okay.
There is the huge story behind it. There's a so we just pick something. The interesting things about pi. But for example, do you know what is pi in the Bible, the Old Testament?
Do what?
No.
Pi. What's the value of pi in the Bible? You'll find it.
I haven't
Old time.
read the Bible.
Yeah.
yet.
If you read Leviticus, when God instructed Moses how to build the temple, they are going to build things for the sacrifice. Okay, it's kind of like a big bowl, huge big bowl. So if you read that in there, the pi, the value of pi actually is 3.
Okay.
And for many practice uses, pi equal to 3 is good enough, right?
Yeah.
But later on, people find that that's not good enough for the things they do, is because the old Babylonians they are trying to find the movement of stars. And when you're dealing with the movement of stars, you have dealing with pies. Okay.
Okay.
And if they're
Really?
pies, hello?
This is really interesting.
Oh yeah. So when you're dealing with the movement stars, if your digit is off, then you'll make a mistake, which is not good. So they have to come up with better accuracy, and they did. But for a long time, they think pi as a rational number, and actually they can get very close. But eventually, people find out pi actually is a irrational number. Like you said, when you turn into decimal, you will never end. And not only you will never end, there's no pattern. There's no repeating pattern. So pi is very, very interesting. So we'll talk about that actually next time. Good?
Okay.
What not only talk about
Good.
pi, we also talk about square root of 2. That's the first irrational number ever proved to be true, and also how they discover it. It's actually the first discovery is more than 3,000 years ago. Okay, it's a very fascinating story behind it. And okay, so we have that, and we also have this. A number times its reciprocal is 1. Okay.
Okay.
Like 4 times 1/4 is 1, or 3 second times 2/3 is also 1. Good. So
Very interesting.
oh, cool. So this is called inverse property. Now the last one is called distributive property. You probably have seen that before, which means when you have a plus, oh, no, the real wrong. When you have a, b plus c, that's the same as a times b plus a times c. Good.
Okay.
Or you have, say, a plus b times c, and that's the same as this a times c plus b times c. Good.
All right.
That's distributive property. Have you seen this before?
Yes, I have.
Distribute. Yeah. How about you, Jet?
Yeah, I have.
So that's the basic rules we have. 10 rules about the operation, about the operators. Then we have a couple rules for equation and a couple rules for inequality, and that makes out the foundation for algebra. Okay, everything is based on that. Good.
Okay.
When you prove something true in algebra, you always have to point back to those. As long as you can point back to those, as long as you are not violating any of those rules, and whatever we call proposition, then that becomes theorem. That means it is proven true. Good.
Okay.
So we have a lot of that. A simple one is this: c squared equal to a squared plus b squared. Good.
Okay.
That's called Pythagorean theorem. Yeah, actually, there's a way to prove it. Okay. All right. Very good. So I'll see you next time. Okay.
All right.